Hi, I'm Kathy. In this lesson, we're going to transform graphs of functions. Our specific objectives are vertical and horizontal translations, stretching and shrinking, and reflections of graphs. Let's start with how you might perform or identify a vertical or a horizontal translation. To graph y equal f of x plus k, what we do is shift the graph of y equal f of x by k units upward. So plus k shifts f of x upward, minus k shifts f of x downward. These two are vertical shifts. Finding f of x minus k is going to shift, f of x k units to the right. Finding f of x plus k, or graphing f of x plus k, will shift f of x k units to the left. These two are horizontal shifts, and again, these two are vertical shifts of the function f of x. Let's try an example. Find an equation that shifts the graph of f of x equal x cubed minus 3x right 4 units and downward 2 units. We'll do that first. When we're done doing that, we'll support this result by graphing. But first, let's find this equation. We want to take f of x equal x cubed minus 3x, shift it right 4 and down 2. If you look back at that beginning screen, to shift this right 4 for each x, I'm going to put the quantity x minus 4. So let's start with that. We'll get a new function. I'll call it f of x also, and I'll replace each x with x minus 4. And that's my shift of right 4. Now, in addition to that, I want to shift this whole function down 2. So outside the function, I'll subtract the constant 2. Well, this is the equation we were looking for. Let's support this result graphically, which means we're going to graph f of x, the original function, and this new function, and see that the new one is right 4 and down 2 from the original. Let's use a graphing calculator to help. In y1, I'll put our original function, which is x to the third minus 3x. In y2, I'll put our translated function, which is x minus 4 to the third minus 3 times x minus 4, and then all of that minus 2. Now I can probably get a pretty decent graph of this on a standard window, so let's choose Zoom, option 6, which is standard. The first graph is the original unshifted function. The second graph should be that function to the right 4 and down 2. And if you compare points like the maximum values, you'll see that they are max and min values, right 4, and the whole function is shifted down 2. That supports the equation that we found by hand. Let's move on to vertical stretching and shrinking of a function. Here's the formal definition. If the point xy lies on the graph of y equal f of x, then the point xcy lies on the graph of y equals c f of x. If c, this constant, is a number bigger than 1, the graph of y equal that number times f of x is a vertical stretching of the graph of f of x. Whereas if c is a number between 0 and 1, think of a fraction like a half or 2/3, the graph of that number times f of x is a vertical shrinking of the graph of y equal f of x. Well, let's try this out. What we're going to do here is graph some functions. We're going to graph 3 functions, y equal x squared, y equal 3 times x squared, and y equal 1/4 x squared in one coordinate system. And we're going to determine from our graph which of the second two is a vertical stretch and which is a vertical shrink of the first function. Let's do this a little bit at a time. Let's first graph x squared and 3x squared and determine, if we can, whether that's a vertical stretch or shrink. And then we'll go back and add in the third function, or graph in the third function. So let's go to our calculator and start by entering x squared, and as a second function, 3x squared. And let's set a little different window than we used a minute ago. Let's set the x min and max to -3 and 3, and our y min to -1, and our our y max to 4. Now we're comparing these two graphs. The first is y equal x squared. The second is 3x squared. 3x squared again is the inner function, and it's roughly taller or stretched from the original y equal x squared. Well, let's go back to y equal, and as y3, put in the function 1/4 x squared. The second function, y2, 3x squared, was a vertical stretch of x squared, so I'm thinking that this y3 that I've just typed in will be a vertical shrink of y equal x squared. Let's push graph and see if that is what occurs. There's 1/4 x squared. Notice that it looks shrunk, it looks shorter, it looks flatter, closer to the x-axis are all ways to describe that function. It's definitely a vertical shrink of y equal x squared. Well, let's continue and talk about horizontal stretching and shrinking. If the point xy lies on the graph of y equal f of x, then the point x over cy lies on the graph of y equal f of cx. Now if c, the constant, is greater than 1, the graph of y equal f of cx is a horizontal shrinking. Horizontal is left to right. Notice that if c is bigger than 1, think of numbers like 2, 3, 4, 5, then that's a horizontal shrink of the graph of f of x. Whereas if c is a number between 0 and 1, think of fractions like 1/2 or 2/3, the graph of y equal f of that number times x is a horizontal stretch of the graph of y equal f of x. Well, let's try an example. This example has two parts to it. We're given a function in terms of a graph. It's a piecewise function made up of two linear pieces. One linear piece runs from -1, -2 to 0, 1. The other piece from 0, 1 to 2, -1. We want to do two things to this graph of f of x, two different things. First, we want to find y equal 3f of x. Now that's a vertical stretch of the function. Think of this as 3 times each y value that already exists for the function. We'll do that in just a minute, but look at the second piece. The second thing we're going to find for this function is f of 1/2 x. Now this is a horizontal stretch, although your thought is to shrink because that's a fraction. Consider this at each x, or as I put an x in here, I have that x, and then find the y. So I'm actually doubling the number of y's. We'll come back to that. Let's start with part A, which is to take the function that we have and vertically stretch it by a factor of 3. So if you consider the original points, I had the point -1, -2, stretching the y coordinate by a factor of 3, I'm going to plot -1, -6, which goes just a little bit off this grid. Then I had the point 0, 1. Stretching that by a factor of 3 means I need to plot 0, 3. And again, I just stretched the y coordinate. This is 3 times each y that is in f of x. I also had the point 2, -1. Multiplying the y coordinate there by 3, I'm going to plot the point 2, -3. And then I need to connect those values. Connecting the first two, I get the first piece of my stretched function, and here's the second piece of the stretched function. Notice how it retains roughly the same shape, but is roughly 3 times vertically stretched. Well, let's do part B. This was a horizontal stretch, actually, of the function. And what we're going to do is horizontally stretch each x by multiplying each x by a factor of 2. So I've taken the point -1, -2, multiplied the x coordinate by 2, and plotted the point -2, -2. Now I need to take the point that was 0, 1 and multiply the x-coordinate by 2. Well, that still gives me 0, 1. And the point that was 2, negative 1, if I multiply the x-coordinate by 2, I plot 4, negative 1. Now connecting those, let's see, I get f of x stretched horizontally by a factor of 2. Well, now it's your turn to try a problem. Here's what I'd like you to do. Given the following graph of f of x, and I'll put it up in just a minute, I want you to sketch a graph of each of the following. First of all, f of 2x, and after that, f of 1/3 x, both horizontal stretches and shrinks. And here's the graph that I'd like you to use. This is f of x. Stop the tape and try to sketch a graph of each of the functions on the previous picture, and restart when you're ready to check your work. Well, let's see how you did. We have this function that we're going to work on. First of all, we want to sketch the graph of f of 2x. This is a horizontal shrink by a factor of 1/2. So we're going to take the points from the previous function, like negative 2, 2, and plot the point negative 1, 2. So start by plotting negative 1, 2. Then I'm going to take 0, 0, and it doesn't matter whether I shrink or stretch that, that still remains 0, 0. And then, again, looking back at f of x, I'm going to take the point 4, 1, and shrink the x value by a factor of 2. So I'll end up plotting the point 2, 1. And I'll need to connect those to get a sketch of the graph of the function. Well, let's do the other part of this example, which is to take the same original f of x, but find f of 1/3 x. Now, f of 1/3 x is a horizontal stretch by a factor of 3. So we're going to take the point that was, let's go back to our original function so you can see what I'm using, negative 2, 2, multiply the x by a factor of 3. So we're going to plot negative 6, 2. So let's see if we can find that here. The next point was 0, 0. The third point was 4, 1. Multiplying the x-coordinate by 3, we're going to plot the point 12, 1. Be careful that you notice, or you pay attention to your own scale. And my scale 1 is halfway through a grid line. Now I need to draw some lines. And I have a graph of this particular function stretched. Close that off. Well, let's continue by looking at reflections of graphs of functions. The graph of y equal negative f of x is a reflection of the graph of y equal f of x across the x-axis. Notice that what's done here is a negative is put in front of the function to get a reflection across the x-axis. The graph of y equal f of negative x is a reflection of the graph of f of x across the y-axis. And what's significant to notice here is that each x has been replaced with negative x. Let's try an example of this. For the given representation of a function f, graph its reflection across the x-axis and across the y-axis. And we have the function x squared minus 2x minus 3. But we're going to go back to a graphing calculator to help with this one, and we'll graph the original function as it is, and first we'll graph its reflection across the x-axis. What that means is I want to graph the negative of this function. Let's see how you can do that on a calculator. First, I'll go into y equals and clear any previous functions and enter the one we're working on, which is x squared minus 2x minus 3. That's the original. If I want to reflect this across the x-axis, I want to graph the negative of it. So put in a negative symbol and then go to your variables button, choose y variables, enter on function, and enter on y1. And so what this calculator now will do as y2 is graph the negative of y1. and we should see the original function reflected across the x-axis. Let's go ahead and use a standard window and see how this looks. So we're going to zoom 6, and there's the original function, and there's that function reflected about the x-axis. Notice that it contains the same x-intercepts. You could even say that that one is upside down from the first. Well, let's go back to y equals and think about in y3 how we might graph the reflection across the y-axis of the original function, which is y1. What we can do on the calculator is go back to variables, go to y variables, enter on function, enter on y1, then next to that put parentheses negative x, close parentheses. So the calculator will take y1, evaluate it at negative x, and graph that. And that's what you need to do when you graph a reflection about the y-axis. So let's go ahead and push graph. We're going to get the first two functions graphed in addition to this new third one. So there's the first two, and here's a third. Perhaps we'll go back to y equals and clear the second function so that it doesn't get confused with looking at the reflection about the y-axis. So there's the original, and there's its reflection about the y-axis. The y-axis is a mirror, and it's a reflection of that. Well, in this lesson, we looked at a number of different transformations of functions. Be sure to work lots of exercises from your textbook for practice.